these massive stars, we see fields of 200 Gauss to 30 kilogauss, so quite a big range. The strange thing is we don't see any fields below about 200 Gauss. There seems to be a cut-off, and then about 90% of the stars have nothing at all above a limit of maybe 10 Gauss. So the white dwarfs, they're smaller, and they have a similar flux. So obviously they have a stronger field, and neutron stars again they have a stronger field because they're even smaller. Now the geometry of these fields, the massive stars, most of them have a roughly dipolar field. Some of them have a field which you can model better with a large quadrupole or an octopole. The white dwarfs, similar. Neutron stars, it's very difficult really to measure it at all. You can measure the dipole component by measuring the spin down rate. Getting an observational handle on the geometry is tricky. But I should point out a fundamental difference here between these geometries and the fields that we see on convective stars like the Sun, or rather the convective part of stars. So we're looking at the convective part of the Sun on the outside, and it's very, very small scale in its structure. The small scale field is of the order of a kilogauss, and the large scale field is of the order of a Gauss. And these non-convective stars are totally different in that they have a large scale field. And how do we observe these fields to evolve? Well, on main sequence stars there's no evidence at all that these fields evolved in time, over a time scale of the age of the star. In white dwarfs, we're lacking evidence of anything. In neutron stars, it seems that these fields do decay on time scales of 10 to the 4 to 10 to the 7 years.
So two questions. The strength variation, the main sequence column there, comes from observation to observation, that variation you're seeing from star to star?
Oh right, yeah. From star to star, yeah.
It doesn't evolve all the time? Okay, and you said that the convective region is small.
How small?
How small, and doesn't it seem like a very ill-posed inverse problem if you only know the strength of the field for a given observation? How do you know how small it is, and how small is it?
How do you know how small it is? You have to ask the sub-evolution people. They have models which they trust. But essentially, the reason why these upper main sequence stars have convective cores is the CNO cycle. So in lower mass stars, the nuclear reactions are mainly PP chain, which depends on temperature as I think T to the 4, and the CNO cycle goes to T to the 15, which means that the energy production is much more concentrated into the centre of the star, and that drives the convection in the centre. For the stars just above that threshold, 1.5 solar masses, is, in terms of radius, I think the convective zone extends really less than a tenth of the radius, and then up to stars of maybe 50 solar masses is less than a third.
You're talking about the surface, the very tiny surface convection zone of the interior?
The interior,
okay.
Yeah.
Because at the surface there's of course also one, which
right.
For the A stars at least, which is very thin, maybe two coupled together.
So I'm kind of assuming that that's energetically
unimportant, yeah. Mm-hmm. And the rotation maybe it's probably differential rotation as well in the core. There's no reason to exclude that. I mean, what are the Rossby numbers? And those Rossby numbers?
In convective cores?
Yeah.
Well, the rotation rates of these stars vary enormously between
so if
12 hours and 100 years or whatever.
So if you have a then the time scales are long. I see. So maybe the inverse Rossby number is too small in a course, and therefore you don't have differential rotation, and therefore, if at all, only an alpha squared dynamo, of course, which is not very effective.
And also, there's the problem of anything that's happening in the core. It's difficult to get the magnetic field onto the surface within a sensible timescale. Okay, so about the formation of these stars. They're all non-convective essentially, but they used to be convective. It's the summary. Okay, these high mass stars, they formed out of a gas cloud which collapsed, and there was a convective phase. The white dwarfs, the high mass ones, are born out of the convective core I just mentioned of these high mass stars. And the neutron stars, so a neutron star forms in a supernova, and just after it forms, it's cooling down rapidly, and it's emitting lots of neutrinos, and that drives convection, and that lasts about 100 seconds, which in neutron star terms is a long time. So what they all have in common is that they were convective for some period, and now they're non-convective. And the magnetic field, well, we observe on convective stars that we have a small scale, churned up chaotic field. But we observe on these non-convective stars that they have a large scale and ordered field. Okay, it's just a silly graphic here. This is a convective star, this is what a non-convective star looks like. Okay, so we've got on a convective star, we've got a small scale chaotic velocity field. And it's not surprising that gives rise to the same kind of magnetic field. On these stars we have either no velocity field or some kind of ordered velocity field. So we would expect naively to have the same kind of magnetic field. Okay, so the obvious question to ask is it possible to predict from first principles what happens to this magnetic field when the convective motion switches off? So I've tried to answer this with some numerical simulations. Okay, so now I'm going to describe this model of formation of these large-scale fields. Right, so the idea here to model what happens when the convection switches off is to run a simulation, a star-in-box simulation, if you like, with an initially turbulent field, which is the turbulence is non-driven, and to see what happens to it. Now, two important properties of this star, which are crucial to the result, is that it's stably shutterfied, which is another word for non-convective, essentially. So importantly, it has a not a biotropic equation of state, so that it's hard to move the fluid element up or down, so you're working against gravity to do that. And also that it conducts electricity inside the star, but not outside. And the initial magnetic field that I used for these simulations was something which you might expect to follow from a convective phase, so some kind of small scale random field. Yeah, and the code I was using with this was like a Northern stagger code, which is a finite difference MHD code. Using Cartesian coordinates, so I'm putting a spherical object into a square box, which makes things easier, whilst wasting some computational expense, but that seems to be a more convenient solution. So what happens then? Well, as you expect, the field evolves at an alpha-n time scale. And what happens is it evolves into an equilibrium, which consists of twisted flux tubes, which are lying at a roughly constant radius. And I'll show you some pictures in a second. Now, one thing to note is that the shape of these flux tubes depend on the initial conditions in the following way. So if the initial energy of the magnetic field is concentrated at the centre of the star, then you get a single flux tube which is just in a circular arrangement around the equator. If the energy is more spread out, then you get a more complicated arrangement. And if you characterise this as the field strength goes as the density to some power, if that power is above some threshold, which is about a half, then you get just a simple circular flux tube. And if it's below that, so the field is more spread out, you get a more complicated thing. Okay, this is what the simpler equilibrium looks like. This is the same thing from two angles. So the axis of symmetry is here. And this is the flux tube going in a circle. Okay, you can see that from the left there. And I'll show you that more clearly here. Okay, so this is the field lines and the initial conditions. So you can see it's a fairly random looking thing. The surface of the star is there. Okay, so that's at t equals 0. And after about 10 alpha crossing times, it looks like this. So it's obviously much more ordered. There's an axis of symmetry, and if I rotate it, it looks roughly the same from each direction. Now, in the case where that's in the case where the field energy is more concentrated into the centre of the star. If we now look at the case where the field energy is more evenly distributed, so there's more energy at higher radii towards the surface, you get something which looks more like this. So this is again after 10 alpha n crossing times. Okay, so it's possible to see that we have some flux tubes. So I'm following one here with the mouse pointer on it. So if anything happens to it here, it turns around and goes back in this direction. So somehow these flux tubes are meandering around the star. So just to remind you where the surface is, it's there. So this is what you're going to see if you look at the star. A load of magnetic field line loops coming out of the surface. But what these two kind of equilibria have in common is that they're both consisting of flux tubes. It's just that in the one case, the flux tube is a circle around the star, and in this case it's a more complicated arrangement, which is random, but it's still a stable equilibrium, so it doesn't evolve on a dynamical timescale. So the first time I showed these pictures to an observer of these high mass stars, he said, "Oh, it looks just like this." So this is one of these high mass stars. So this is actually quite a bright star, which you can see probably even from Stockhaven's magnitude 2.8. And the advantage of these stars over the compact stars, obviously, is that you can observe them a lot more easily. And you can look at the Zeeman effect and use that in combination with the Doppler effect as the star is rotating, and build a map of the magnetic field. And so this is what you see, and you see exactly the same kind of thing as in the simulations. These loops coming out of the surface. So that looks like flux tubes sort of meandering around in some apparently random arrangement. If we take a closer look at the structure of these equilibria. So this diagram shows the two kinds, the axisymmetric equilibrium and the non-axisymmetric. This is a cross-section of one of these flux tubes. The red shading represents the toroidal component, which is the component into the screen. and the lines represent the toroidal component. One of the important points to note is that the toroidal component is entirely confined to the last closed toroidal line within the star. And the reason for that is that if you had toroidal component out here, then your field lines would be going into the star and then twisting around, and then coming out the other side. Because the field outside of the star is a potential field, so it's zero current essentially. It would be rather like taking an elastic band, twisting it, and then letting go of the ends, and obviously it would untwist. But in this region, the elastic band is connected up to itself, so it can't unwind. Okay, so that's what these two have in common. The only difference really is that this angle here, which I'm calling alpha, in this case is pi. And it's possible to calculate what this angle should be in the following way. Okay, so you calculate the energy of this magnetic field in this flux tube, which is just, so this is just the area on the surface of the star, the tube. The radius of the star is an 8 pi here with a factor of 3 in geometrical considerations. And then that's just the three components of the field. Toroidal component, the longitudinal, which is this way, and the radial, which is this way. And then you can think of allowing the tube to either lengthen and become thinner, or contract and become thicker, and see what happens to the strength of these three components. And these are the derivatives with respect to this angle alpha. So to minimize the energy, take the derivative of the energy in the normal way, and then you find that the toroidal component and the longitudinal component are equal to each other. And because θ is 0, you have this relation with the radial component and the angle alpha. Okay, so this is the relation of these strength of these three components here. So in other words, if you give this a too strong toroidal component, then the tube will simply contract and become wider until these are in equipartition, and the converse. And it turns out that the angle should be of this order, where that's the toroidal flux and that's the toroidal flux in this tube, which are conserved on a dynamical timescale. Okay, so this is a little animation following the output of one of these simulations at a particular moment in time. So what we're doing here is following a single flux tube around the star. This is the centre of the star, and this is the surface. And this is the flux tube that we're following. The shading represents the toroidal component, the component into the screen. And you can see some neighbouring tubes like here and here. Okay, so now we switched from one tube to another there because of some kind of issue with the algorithm that follows the tube. But anyway, so you can see that it's definitely not terribly regular, but it's despite being in equilibrium. Right, so I'm going to just say a few words about magnetic helicity, which is a useful tool in understanding what's going on. So in initial conditions of this, well, they're constructed by just combining. So the idea is So the idea is to have a sort of turbulent-looking field with a combination of length scales, and they're combined in a random fashion up to a maximum wave number, which I'm calling K max. Okay, and you can run this simulation with various different values of this maximum wave number. So the power spectrum is flat, essentially. And what happens if you do this, and then plot the magnetic energy against time? Okay, so these are 4 different runs with these 4 different values of this maximum wave number. And they all start with the same energy. And the runs with the lower maximum wave number end up with a larger energy. So what's happening here is that this is, okay, so these are sound crossing times, which is about a tenth of an alpha crossing time. So the equilibrium is forming at around this point. So the gradient of this change is energy dissipated on a dynamical time scale. And from here onwards it's on a diffusive time scale, which is something different, which I'll come on to later. Right, so if you start with a field which is structured on a much smaller length scale, you lose more energy in reaching this equilibrium. And you can think about it in terms of this quantity magnetic helicity, which is defined as simply as the volume integral of the field with its vector potential. And the useful thing about this is that it's a conserved quantity, well, at least in the limit of infinite conductivity. And now if you plot the graph of this quantity against time, you see that they start with different values of helicity. And the helicity falls by a comparable amount before it reaches this equilibrium. So it seems that it's perhaps possible to predict the energy of this equilibrium if you simply measure the helicity of the initial magnetic field. But it might not be quite as simple as that, because it seems that it's possible also to fall into an equilibrium with zero helicity in the following way. Okay. If we look at this field here, okay, this is a cross section of the star, consisting of 2 flux tubes. So it has 2 of these circular flux tubes on top of each other. And the polar components are arranged so that it's continuous at the boundary between these 2, which is here. This is the axis symmetry of the star. And the shading represents the toroidal component. So it's in opposite directions in the two flux tubes. And since the polar components are also in opposite directions, and the helicities of these 2 flux tubes are of the same sign, which is because the helicity can be thought of as just the product of the toroidal and polar fluxes. Now what you can do is simply reverse the toroidal component of one of these tubes, which has no effect on the stability of the system, because these 2 tubes don't even know which direction their 2 toroidal components are in, because they're disconnected from each other. But what you've done then is reverse the sign of one of the helicities of these tubes, and so you've got a zero net helicity. So that's like having a local energy minimum rather than the absolute minimum. So it's possible that you can fall into one of these local energy minima, which would mean that you can't really predict the energy of the equilibrium just from looking at the initial helicity. So there's obviously more work than that is required to see what's going on, and whether you can form one of these helicity equilibria. Right, so next thing then, I'm going to talk just about the axisymmetric equilibrium now, because it seems that many, if not most, of these non-convective stars do have roughly axisymmetric equilibrium. And the useful question to ask is, what is the ratio of the 2 components? Now both of these components are unstable on their own, and you need both of them for stability, which I can so I can show you the result of okay, this is a simulation where we have just a poloidal field on its own. So this blue thing is the star, and this is the boundaries of the computational box in white. And this simulation runs for several alpha n crossing times. and obviously it's unstable, but it's decaying on a dynamical timescale. So that's what happens if you have just a colloidal component. And a similar thing happens if you have just a toroidal component of its own, so just an azimuthal field.
I mean, can you actually check in this case that you really have an exponential departure from the initial equilibrium? First of all, if you have an equilibrium initially, perturb it by a certain controlled amount, you should expect an exponential departure from this initial state.
Yeah.
Can you actually verify that and get a growth rate?
Yes.
Uh-huh.
Which is of the order of, well, it's
so it's not
factor of order unity.
Yeah. So it's not a resistive decay; it's a dynamically enhanced decay. Yeah. Mm-hmm.
Although I can't rule out that if you run this simulation for long enough, that it will not find its way into some kind of zero helicity equilibrium or something.
It has, of course, zero helicity to start with, right?
Right.
Yeah. So it will have zero helicity in the end. That one.
Yeah, but it might find its way into an equilibrium at some point, or it might not. It's just that it doesn't seem to be doing that yet.
Mm-hmm.
It continues to evolve on an alpha n time scale for a long time. Right, so a purely colloidal field is unstable, and also having a very strong colloidal field in relation to the toroidal component is also going to be unstable for the following reason, and that is if you cast your mind back to the equilibrium value at this angle in the non-axisymmetric equilibrium given by the flux of the toroidal and the colloidal. So if you increase this colloidal flux too much, then this angle alpha will want to go down below its value of pi in the axisymmetric case. So what you'll see is simply a transition to a non-axisymmetric equilibrium if this colloidal component is stronger by some factor of order unity. But the converse cannot be said, because this angle alpha cannot go above pi, obviously. And in these simulations with random initial field, what we see actually is that the ratio of the colloidal energy to the total is a fraction of between 5% and 10% roughly. But we can see exactly what the range of possible ratios is with the help of simulations. Okay, so these are some simulations which I've run simply by taking the output of the random initial condition simulations and changing the ratio of these two components by hand. So this is a simulation where this ratio is 0.9, so the colloidal energy is 90% of the total, and at 3 points in time, this is in terms of alpha n crossing terms. Okay, so we get an m equals 2 mode growing, and then it saturates. So this is the new equilibrium. Okay, so it's gone into a non-axisymmetric equilibrium, and it just stays there. This ratio is only 0.7. After the same number of alpha crossing times, we have, well, nothing's happened at all. And it turns out that the ratio is at about 0.8, which is within our prediction of a factor of order unity ratio between the two. Now, conversely, if we try with a strong toroidal component, so a toroidal component on its own will suffer the following kind of instability. So if you imagine, okay, so these are equipotentials. This is the star. These are equipotentials, and we have, if you like, sort of magnetic rings. Okay, and they're exerting pressure on one another because of the nature of the Lorentz force is that you can think of these rings as exerting pressure on each other, and they have a sort of tension. And we see this kind of instability. Okay, so it's rather like well, if you're trying to carry something really, really heavy, then you get one of your vertebrae might slip out of equilibrium. But it's the same kind of thought. So these things are all pushing on one another, and then obviously the easiest way to release that pressure is if they move sideways. And Taylor derived some stability conditions for sensibility, which I'll go on to now. Okay, so what I just showed you in the diagram was the m equals 1 mode, so that's the whole loop just moving sideways. There's also an m equals 0 mode, so an axisymmetric mode. Now if we plot a cross-section of the star, so this is the axis of symmetry of the star, and this is the equatorial plane. Okay, so this line here is the last closed toroidal line. So the toroidal field is entirely confined within this space. If we work out what Taylor's stability conditions give us, we find that the area outside this blue line, so that means this area here, should be unstable to the m equals 1 mode. And then likewise for the m equals 0 mode, the area outside this green line. So the toroidal field outside this area is 0. So that's just considering the toroidal field on its own. But the toroidal field can be stabilised by adding a polar component. So if you imagine in this kind of picture, if you add an extra field component going through all of these loops, then it will help to stabilise the field. Because to move sideways out of equilibrium, we'll have to stretch that component, requiring energy. So that's a stabilising influence. And you can do the same with a if you imagine adding a radial component of the field to this star, you can work out some kind of stability condition here. So this is the radial component of the field, that's the toroidal component, and this is some kind of length scale in the radial direction. And that is the radius of the star, essentially. It's a little bit uncertain exactly what these numbers should be, but just to give you a rough idea. Okay, and if you do this for a particular output of this simulation with random initial conditions, where the toroidal energy fraction is this pretty small value. Okay, so this is the output of a random initial conditions simulation, where this ratio has been changed by hand, if you like. And if you apply this condition, you find that the field in this region here, outside of this thick pink line, has been stabilised. So there's still an unstable region. If we increase this ratio a bit, we find that the stabilised region has also grown. And if we increase it more, we find it's growing quite a lot. So it looks like this case is the roughly borderline stable region. And to confirm this, what you can do is simply set the simulation running with that ratio of the field strengths and see what happens. Either it's unstable or it's not. So I've done this with 3 different initial conditions. So these are just, well, this field is concentrated in the centre of the star. This is a bit more spread out, and this is, well, most of the flux goes to the surface here. And the lower limit on the toroidal field is found to be of the order of a few percent. So the case I just showed you with the cross sections was this case, where it's about 1%. So it seems that you only need a fairly weak boloidal component to stabilise the toroidal field. Yeah, and as I said before, the upper limit on the boloidal fraction is about 80%. So that it seems that the toroidal component can be a lot stronger than the polyidal, but not the other way around. Okay, one of the interesting reasons for studying this at all is that a magnetic field can deform a star through the Lorentz force. Now, a predominantly polyidal field, so with a high ratio here, produces a star which is oblate, and conversely a toroidal field produces a proto star. And if you set this star spinning, it should precess. So apparently the Earth does the same thing. There's a torque-free precession of the Earth, which is called the Chandler wobble, which has a period of 14 months. Right, and there's some friction, so this is damped. And obviously, anywhere there's any dissipation of energy, the system will fall into a minimum energy state. And if you conserve the angular momentum of a rotating body while dissipating its energy, it will want to rotate around the axis with the highest moment of inertia. And the result of that is that a star with a predominantly polyidal field will end up with its magnetic and rotation axes aligned. Conversely, toroidal field will produce a perpendicular rotator. And one of the most interesting things about this, about a star which is rotating with its axis not aligned, is that it will emit gravitational waves, which in the case of a neutron star may be quite interesting, particularly because so one of the scenarios where those might be detectable is if you have a supernova and then you produce a neutron star which is rapidly spinning and has a strong magnetic field, then it may emit a significant amount of energy in gravitational waves, which ought to be detectable within the foreseeable future, as always. But this is ignoring any external torques, I should say, so that's something else which needs to be considered. And another reason so it's interesting to ask about the ratios of these two components is that, well, especially in neutron stars, okay, you're observing just the dipole component. But there are various energies why this might be an underestimate for the total energy. One is that you might have a non-axisymmetric equilibrium, so you've got energy in high monopoles. If you do have a roughly dipolar field, then you can have the energy concentrated at the centre of the star. Or you can have a very, very strong toroidal field, and the toroidal field you can't see on the surface, because only the polyidal component goes through the surface. So this may be one reason, perhaps, why we see neutron stars which have the same spin period and the same dipole field strength, which have very, very different observational properties. So some of them are emitting mainly in radio waves, and some of them mainly in X-rays and gamma rays. So I just wanted to say a little bit then about how these equilibria evolve in time. So there are various processes how this can happen on a much, much longer time scale compared to a dynamic time scale. So the most obvious one is the atomic diffusion, simply because these things are not perfect conductors. The time scale at which this happens on is independent of the field strength. Then there are buoyancy effects, which I'll explain in a second. And the time scale that these operate on goes as b to the -2, so the stronger the field is, the faster they go. And then there's Hall drift, which is essentially a result of if you think of the field being kind of frozen into the fluid instead of an MHD, or an ideal MHD. If you include this effect, it's frozen into the charge carriers, not into the fluid as a whole, which is negligible in a main sequence star, but probably quite important in a neutron star. Okay, so this buoyant process I mentioned. So how does this work? So if you imagine a magnetized region of the star, one of these flux tubes surrounded by a less magnetized or non-magnetized region, they're going to be in pressure equilibrium. Okay, so the pressure, the thermal pressure inside plus the magnetic pressure inside this region has to be equal to the pressure outside. If this thing is not to rise or fall on a rapid timescale, we need the densities to be the same as well. And if you think of an ideal gas, densities are the same, but the pressure inside, the thermal pressure inside is less. Then obviously you need the temperature to be less as well. Or in a compact star, you need a composition gradient, composition difference, which means that you've got a lower electron fraction inside this magnetized region. But you have inevitably some diffusion of heat or particles into and out of this tube, and the result of that is that the tube will rise on a diffusive timescale. Right, and as this happens, the toroidal flux will be lost faster than the poloidal, because the toroidal flux has to be confined to this last poloidal closed line. So as that line rises, all of the toroidal flux on it will be lost. How important are these processes in different kinds of stars? In the main sequence stars, probably none of these are going to have any effect on a sensible timescale. In a white dwarf, the M dissipation may be interesting. The composition gradient in a white dwarf may be pretty important in actually holding this field in the tool. But the thermal, the heat, the thermal aspect probably not very important. And the Hall drift is not very well understood. In neutron stars, probably the most important processes are the buoyancy process and the Hall drift. Simply because a neutron star is smaller, the Hall drift has a greater effect, because the drift velocity compared to the size of the star is greater. So what's the result of these processes? Well, they all seem to have a similar effect, and that is that you move along a sequence of equilibria. Okay, so all of these are all equilibria, and they can all be reached on a dynamical timescale given the right initial conditions. In this equilibrium, we have a field which is fairly well buried into the star, and it's an axisymmetric, roughly axisymmetric equilibrium. Here we still have an axisymmetric equilibrium. This is closer to the surface, this flux tube. So more of the flux goes through the surface. Here we have a non-axisymmetric equilibrium, where the flux tube is doing something like that. And here we have an even more complicated thing, where the flux tube is doing something much more chaotic. And the result of these diffusive processes is that you move along this sequence. So ohmic diffusion just makes everything spread out, and the buoyancy processes bring everything to the surface. So it's natural that you go from this to this. And then, because the toroidal flux is being lost faster than the poloidal, then you make this transition, as I mentioned earlier, to the non-axisymmetric equilibrium, and then it becomes more and more complicated at implementing. So I'll just make some brief conclusions. Right, so there seems to be a continuous sequence of equilibria which are stable on a dynamic timescale. All of them consist of twisted flux tubes. The difference is in which pattern they're in. And diffusive processes make the magnetic field move along this sequence in one direction. You can produce one of these equilibria given a turbulent initial field, and depending on what kind of field that is and what its radial energy distribution is, you can land on any point of the sequence on a dynamical timescale, and then it evolves along this sequence. Yeah, and in an axisymmetric equilibrium, the colloidal energy fraction can be in this kind of range, roughly speaking. But it seems that a low energy, a low colloidal energy ratio is more likely, meaning that, well, in the case of neutron stars, meaning that the damping processes will tend to produce a perpendicular rotator, which is a nice result in terms of gravitational radiation, because obviously a perpendicular rotator will have a greater quadrupole moment. So just some things which need to be answered in the future. Also, yeah, an obvious question to ask is, well, on convective stars, we see that the field strength is a function of things like the rotation speed. There are some nice correlations there. Why is it that in this, once convection switches off, the field is not a function of rotation speed or anything like that? There are, if you look at different objects of the same type, the field strengths have ranges of several orders of magnitude in all of these classes of convective star, non-convective star. So in these high mass stars, we've got an added peculiar phenomenon. There's a cutoff at 200 Gauss, which is unusual. So below that, you don't see anything at all between 200 Gauss down to the detection limit of a few Gauss. Yeah, so some more quantitative work on exactly what the field looks like after this convective phase would be useful. So the effect of the length scales involved and helicity and so on. Gravitational radiation from neutron stars. So there's a millisecond magnetite theory which essentially says that neutron stars with very, very strong magnetic fields are the result of supernovae where the neutron star which is born is spinning extremely quickly, and so you have a strong dynamo producing the strong fields that you see on some of these stars. And that competes with the theory that the strong magnetic fields are simply left over from the Genesis star. And if you see gravitational radiation from one of these really fast spinning stars, then you'll be able to distinguish the two theories. Yeah, thermal conduction is non-isotropic in a strong magnetic field, which should be detectable on a neutron star. And if you know what the geometry of the field is, you can work out where the temperature should be higher on the surface and where it should be colder. And last but not least, so these objects called SGRs, which are highly magnetized neutron stars, they undergo occasional sort of outbursts where they emit a load of X-rays. And you see oscillations in these flares, some of which are thought to be Alfvén modes, so standing Alfvén waves propagating through the star. And obviously, if you want to calculate the frequencies of those and what's going on, you need to know what shape your magnetic field is. So there's some connection there with some other work going on. So that's all I want to say. Thanks.
Questions?
One of the slides near the end, you showed a bunch of different equilibria when you were talking about these various mechanisms, for example, buoyancy versus the Hall effect. Yeah. What's known? You made a general argument about the buoyancy effect. What's in the calculation that accounts for the effect of double diffusion?
So a combination of magnetic diffusion and thermal diffusion.
Compositional and thermal.
Not compositional, no.
Uh,
But it's logical to expect that the thermal will have a similar effect to the compositional.
Why?
Because this buoyancy effect. I mean, so if you have so in this magnetized region, you have either if you have uniform composition, then you have to have a lower temperature, and if you have uniform entropy, then you need a heavier composition, and both of those, heat and composition, is linked to diffusion.
Yeah. But one is usually enormously faster than the other.
Right.
Right. So I mean, so you can have a stable stratification as an initial value problem, which is controlled by the major component of the equation state,
Right.
but due to diffusion, differential diffusion of the two species, whether it's heat and composition or heat or something else,
Right.
can give rise to a buoyancy-driven convective instability. It's called double diffusive convection.
Well, you've got the convection layers or salt fingers and that kind of stuff.
Yeah.
Right. In a main sequence star, I don't think the composition gradient is going to be as important as the entropy. And a neutron star, I think the composition gradient ought to be a lot more, ought to determine the dynamics of these things.
So you are concerned about the case with magnetic field? Why he says there's an instability, or what is the concern?
I just don't know what equations are being solved to produce what's called buoyancy.
Yeah.
That's.
So it's
in these simulations,
it's
there's
of course
no
the
composition gradient, so it's just heat. Yeah.
it's a magnetic field which is active and therefore constitutes a component to the pressure, or at least to the pressure
I
balance.
understand that. Yeah.
Yes, and therefore it reduces the pressure in the tube.
I understand that as well.
Mhm.
Yeah. So, but that's a different effect than compositionally driven instability,
Yes.
which is what I'm asking about.
Yes. But he may not have that, right? Or why should he have that?
He brought it up. I'm just asking.
Oh, is that right?
Yeah,
You brought it up. I didn't hear that.
Okay, so I'm just speculating that the effect of composition gradient will be comparable to the entropy. Yeah. That you would think that they both work in the same way, and if you have both of them, then why wouldn't they just add together? Okay, one of them is probably going to be more important than the other.
I mean, you have also conduction maybe of these compositional concentrations along field lines preferentially. Is that true? Because they are, of course, charged only, I guess. Right, but they will be all charged.
Right.
So then there will be conduction again preferentially along field lines. Compositional conduction.
There must be some condition to work out whether that's important or not on the different length scales. Well, in a main sequence star, it's not relevant because of the main free path.
Mm-hmm. Yes. Must be in free path must be long, right?
Right.
Yes.
My guess would be that the same is the case in a neutron star with the composition.
Yeah.
Any more questions?
I mean, your initial field is constructed by random initial conditions, right? But you also started off initially by saying that you motivate this by the end result of a dynamo that turned off, because the convection turned off. Now, in the cases when a magnetic field is driven by a dynamo, there would indeed be helicity because of stratification and rotation. But this helicity, like we have on the Earth, we have cyclones and is opposite helicity on the northern and southern hemisphere. So in a star that would also work, of course, and that's exactly what produces, of course, large-scale magnetic fields. But they would be exactly of that second configuration that you plotted, namely the one which had the opposite helicity on the two hemispheres.
That's a good point.
So therefore, a generic initial condition may really be one where you have very close to zero in net helicity. Because the fact why you have these configurations here, of course, at the end of the decay, is because it's the helical component which is conserved and cannot decay. Everything else decays, and it's this one which remains. And if you started this initial condition from a dynamo, even this may vanish. Of course, that's a problem or possibility.
Right. So maybe you end up with an equilibrium with more than one flux tube of the opposite side.
Yeah, but they would cancel across the two hemispheres over the duration of the calculation, because you have net zero helicity in this. I mean, unless the two hemispheres remained, of course, decoupled for geometrical reasons.
Well, you can appeal to observations and say that most of these stars have roughly dipolar fields.
Yeah, but
So there must be some net helicity.
but even they have helicity which is antisymmetric, because the toroidal field will be of opposite sense in the northern and southern hemispheres. I mean, at least in the initial condition.
The equilibrium is. That's not the case. You've only got one toroidal field.
Yeah, but that's in your simulations, right?
Sorry?
That's in your simulations.
Yeah.
Yeah, and those have been started with a net helicity, of course.
Right.
So if you started the same with zero net helicity, then you would have oppositely oriented toroidal tubes,
Right.
as you would have in the Sun, for example, and the Earth. And then that may all be gone, of course, by the end of the calculation.
So maybe that's the reason why some stars have dipolar fields and some unconjugated ones.
Perhaps also, yeah.
Any questions? Maybe I can ask one about this picture. If you see this as a sequence, can you tell if the exterior observable, if you think about interstellar, dipolar polar field, can you say if that can grow with time? Despite
if you go from here to here,
yeah, because it looks like the magnetic
possible the fluxity on the surface does increase, yeah.
So you could imagine that.
You could imagine an increase with time.
So that could explain, say, these transient pulsars, whatever they call them.
RRS or
RRS and Magnificent Seven.
Right.
What the fancy names.
It's not inconceivable, yeah, that the field strength goes up.
Despite
And then
losing
you see-
magnetic energy.
Yeah.
Is there no further question? Thank you, Anton, again. And now it's eclipse time, I think.
Right.
Eclipse then?
Sorry?
Is it an eclipse? A partial
Maximum
eclipse?
in 5 minutes.
Today? No.
No. Amazing. Yes, I know, I remember. You know, you want to turn it off, you press twice. Yes. So my computer crashed, that's amazing.
You take on the thingy as well.